Oh, you know what? Hold on one. Week, because I don't think I have enough to go and give you something cool every single day, but I'll try to give you something cool every single week. All right, I just decided that right now. I've never done that before, so hopefully I can follow through on it. All right. If not, if I can't think of anything, then we'll just watch a pitch meeting on YouTube. All right, those are incredible. So, screen rant. So, sample variance, this lovely looking formula, and population variance. Lovely looking formula that looks pretty much the same. All right, one of them is dividing by n minus 1, the other is dividing by n. All right. The n minus 1 represents something called degrees of freedom. And so there's a lengthy explanation and lesson behind why that works the way it does and what it really is. So different story for a different day. But there is a good reason why there are two different formulas depending on whether it's a sample or a population. All right. So I'll pay that off down the road. So we're going to compute the sample standard deviation, which is the square root of variance. All right. In order to do that, the first thing I need is the mean. All right. Now, this is kind of one of those tricky situations where we're going to use the calculator in some cases to just run some rote calculation. Or I'm not going to, but you might consider doing that. And immediately follow that up with, well, if I'm using the calculator for this, why wouldn't I use it for that? All right. The rationale there is that I'm going to show you the inner workings of standard deviation, and then we'll do it on the calculator after this. All right, so I'm going to take the sum of my x column. So 5, 11, 14, 28. 7 values. So x bar is going to be 28 over 7, which is 4. All right, so I create a column of x bar. You don't actually have to do that, create a column just to write the number 4 repeatedly. I'm going to do it just so I can have stuff to point to with my pointer. It's a lightsaber, in case anybody's wondering. Okay, not impressed. Got it. Cool. I mean, has anybody ever seen a presentation in a class where the teacher used a lightsaber as their pointer? Okay, I just needed someone. I just needed someone to help me. Yeah. All right. So x minus x bar is my next calculation. Now, I'm kind of modifying the formula here because it's x sub I minus x bar, but I don't want to get bogged down with the notation. All right, the subscript is just telling us the position within the data set. So if I said x sub 2, I'm talking about the second entry. But since we're doing it for the entire table, I don't need to distinguish one from the other. All right, so we're looking at -2, -1, +2, -1, +2, 4, and -4.
Could you also do absolute values there?
You, as part of the next step, you could.
Like in this column, could you just do
Yeah, because you can square it anyway. Yeah, so if you drop the negatives, that's totally fine. All right. This column is the deviation. All right, this column is the deviation from the mean. All right, deviation is talking about distance, so how far each data point is away from the mean. But I want a number that's going to represent the overall spread of the data set, so I want to keep going. All right, so x minus x bar is going to get squared. So 4, 1, 4, 1, 4, and a couple of 16s. All right, the summation is telling me to add up all the entries from the first entry to the nth entry, so it's saying all the entries. So I'm going to take the sum of this column. so 10, 14, yeah, 46. All right, and then we're going to multiply that by 1 over n minus 1. All right, so n is equal to 7. So my s squared is going to be 1 over 7 minus 1 times 46, which is the same as saying 46 over 6. You could reduce it if you want, but since I'm looking for standard deviation, my next step in the process is going to be to take the square root of that. All right, so you can leave it in whatever form, because we do, at some point, have to put it in the calculator. And so we'll go 3 significant here. I guess you don't need to see me taking square roots and stuff. So we're talking about 2.769. But you could see, when you look at the table here, you can kind of get a better sense of why we're doing what we're doing in terms of the formula itself. So, yeah, we got the number 2.769 not very spread out. Okay. Or maybe, depending on what the comparative values are. But it's a small number, so we could assume it's not overly spread out. But here we would get the idea that we have distances away from the mean. Some are below, some are above. All right. If I were to just add this up, because what you say, why square it? Well, if you add this up, we have negatives. Negatives could balance out the positives, and you might walk away thinking that in some cases that you have a standard deviation of 0 when the data is actually pretty spread out. All right. So squaring it actually allows us to come up with positive values that are consistent, bless you, with the deviations, which we correct for later on when we take the square root. All right, so we're leveling up here to level back down later on. All right, so it's a canceling operation, so it's perfectly fine. The big question I usually get when it comes to standard deviation is, all right, well, there's other ways that you can get rid of negatives. Instead of taking the x minus x bar and squaring it, couldn't we just take the absolute value and then add those values up? Yes, it would be something different called the mean absolute deviation, which is perfectly fine. But the standard deviation approach is derived from a normal distribution. All right? So if data are normally distributed, then it's measured in terms of standard deviations away from the mean. All right? So since the world at large is generally normally distributed, or could be converted so that it is, it'll always work out if you use standard deviation, so that's the justification there. Right? And so you might look at it and say, well, no, the world is not normally distributed. It's skewed in some cases. We could actually use approaches to take a skewed data set and convert it into a normal distribution. So something that actually tails off to one side, I can manipulate that data set so that it's centered around a mean. All right, and so that's a different topic for a different day. So for frequency tables, I'm just going to kind of cut to the chase. I'm not going to write the table, but I'll take you through the table approach on your calculator, because now we're incorporating a frequency. All right, so 1, 2, 3, 4, 5. Yeah, that is on. And then 10, 3, etc. So 10, 3, 1, 8, 5. All right, the first move is going to be to find the average. All right, so something important here, if I try to find the average just by adding up the x values and dividing by 5, it's going to be misleading. All right, what I need to do first, in order to find the average, is multiply each x value by its frequency. All right, multiply each x value by its frequency, because the 1 occurs 10 times. So there's going to be a total of 10 if I were to add up all those ones. The 2 occurs 3 times, so that's 6. 3 occurs once, and so on. All right. So that's what I have to do, but I'm going to let the table do it for me. All right. I don't want to write anything. I didn't even want to write that down, but I don't want to write anything down except for the final answers. So x times f. So in L3, we're going to do L1 times L2. Now you could find the sum on the fly, so you could just add it up in your head, but you could also use the sum feature, all right? So again, that's second stat math 5. I need 2 values. I need the sum of all the values in L3, all right? And I need the sum of all the values in L2. All right, so divide those 2 numbers. Not the nicest looking decimal, all right? Do I want to round that? The answer is no. Do I want to write that entire decimal out just to type it back in the editor? No. So this is what I'm going to do. I'm going to store it. I'm going to hit that store key, STO, right above on. One of the many keys that you hardly ever use. All right, it's right next to 1, right above on. STO with the sideways arrow. Hit that and use any letter that you want. I'm going to use A. So alpha math to bring up the letter A. All right, what that's going to do is allow A to represent that number. So anytime I type the number A, it's going to bring that number stored in. Unnecessary step, kind of, because you could also just use the fraction, 76 over 27, as your mean. It's more exact. You don't have to worry about rounding. But we're gonna learn about storing values and how that can be useful down the line anyway. So it's worth looking at now. So stat edit. I want the mean in there. So L4 is going to be equal, really it could be L1, 2, or 3 because it's just getting multiplied by 0. So L1 times 0 plus A. All right. So again, my goal is to do all of this without having to write down anything, all right? So, except for the answer. So I'm still trying to stay within that framework. You might want to write down like little reminders to yourself, do this, the store key is for that and stuff like that, but that's up to you. All right. The formula tells us that it's x minus x bar still. All right, we still have to do that, but then we have to take that result and multiply it by the frequencies. All right. The biggest challenge when it comes to using the table approach on the calculator is just remembering what column's what. All right. So you just got to be focused on it. Any distraction and you can kind of lose it. All right. So I'm going to do L1 minus L4. That's going to give me the deviation from the mean. All right. So only 2 values, according to this, only 2 values are below the mean. The rest are above. Check your data set, make sure that's consistent. That's true, so we're good. We're going to multiply these values by the frequency column, which is L2. Now, I lost my L6 along the way, so I'm going to just put it back. So second 6, enter. Now I have my L6. All right. So I'm going to take these values and multiply them by the frequency values. Go to, I put it in the wrong, you see that'll happen. If you put it in the wrong place, you'll get an error message. It's got to be right on the L6. So L2 times L5. All right. So remember that deviation of negative 1.815 occurred 10 times. That's why you're getting that product. All right. Now, we're all out of lists here. So if I needed to go further, that might be a problem. It's not a terrible problem. I'll show you how to handle that in a sec. But we have just enough lists for what I want to do, so we're good. But let's say you wanted to continue your table. You needed to do some other things with it. All you have to do is name it. We're out of L's. We're out of the pre-installed lists titles. You call it whatever you want. All right. So if you want, you could give it a name. Right, so you could say more or something. I don't know, just made up something. All right, now you might look at that and say, but wait a minute, what if I needed to find the sum of my more list? That's all right, because you may have noticed this, if you hit second stat, all of your lists are there, even the ones you come up with on your own. All right, so if I needed to take the sum of my more list, I would just click on this. You see it has a little L next to it, indicating that it's the list called more. All right, so you can handle it that way. But ultimately, I don't need that. So I'm going to do second stat, math 5 on my L6. Okay, where did I screw up? Did I not square it? I didn't square it. Oh, okay, so that's an example of what would happen if you didn't square your data. Right? You got the negatives balancing out the positives. So actually, I do need my more list. The other option would be to combine steps. And in L6, you could do L2, in parentheses, L2 times L5 squared. All right, to bang it all out. Okay, so let's, because now it went from optional, nice to know, it went from that to required. So let's do that again. So you have a list, a blank list. What you want to do, so right here, is just hit enter on it and then name it whatever you want. All right? So just throw in a string of characters and you'll be fine.
You puke.
Oh yeah, why not, right? There you go, you puke. Okay, so, oh, I don't need these. I accidentally hit the Y equals, so now I feel obligated to clear all this stuff out anyway. All right, so in my extra list, what I want to do is hit enter and then just say L6 squared. All right. So now I need my sum of, I actually need the sum of my more list. So second stat, math 5, then second stat, option 7. Now I have the sum of that very last column. I'm dividing it by the sum of f minus 1. Now I just happen to remember from before that the frequency column added up to 27. So this has got to be one less than that. So divided by 26. And that's going to give me my, actually the most exact form that the calculator can produce, sample variance, rounded to 3 significant, 20.948. And S is going to be the square root of that. I'm not going to take the square root of the rounded value. I'm going to take the square root of the whole shebang. And so we'll be looking at approximately 4.577. So you look at this and you say, I don't know if that's a big number or a small number, but you do know it's bigger than the one that we got for the previous data set. All right? So compare this to the previous data set just by looking, not even like anything crazy. You look at it and say, well, this one went from 0 to 8. All right, so the range is pretty large, but it's not like you have values that are produced more than once. Like, oh, except for the 3s and 6s, but it's pretty consistently in that interval. But here it seems to be kind of more like all over the place. All right, if this 10 were smaller, you know, making it a more balanced distribution, then you might say, yeah, it's not very spread out, but because there's 10 of those ones, it's really kind of pulling the data in that direction. All right. All right, so linear transformations. In some cases, it makes sense to transform a variable by a linear factor. This results in the following. Multiplying each observation by a positive number, B multiplies both measures of center, mean and median, and measures of spread. right? So that's important, because if I were to take just that first data set, I'll keep it simple, and double every value, you would expect the mean to be double. But what you might not expect is that the spread is also going to be double, all right? So, or at least in the neighborhood of double, right? Sometimes there's a little iffiness to it. Adding the same number A to each observation adds A to measures of center, but does not change the measures of spread. This goes along with what I was talking about last time, where these rules are great. I don't even need to put it in. These rules are great, but let's say you're taking a test and you completely forgot. Then what?
You just do it.
Just do it. Yeah, just make up a data set and just, well, some of you, I guess, but yeah, you just add something to each value, the same number to each value, see what happens. All right, stat calc 1. You have the ability to invent these rules on the fly. All right. Most of the time, people go in being like, I know it's going to change the mean, not sure what's going to happen to the standard deviation. So that's when coming up with a data set on your own. Okay, so now a foray into the Greek letters. But fortunately, we're not really leaving the world of measures of center and spread, because you're dealing with mu representing the mean and sigma, lowercase sigma, representing the standard deviation. So the squared value would be the sample variance. All right. So the first property, if you add or subtract a constant to each piece of data, the mean will get that same constant added or subtracted. If you add or subtract a constant to each piece of data, the variance will stay the same. That's what I was saying before. Suppose an exam is given and the mean is 55 and the variance is 10. Suppose 5 points is added, whatever, I don't know, is added to each exam score. The new mean and variance be what and what? 60 and 10. They love these kind of questions on the AP exam, which means I love them on my unit tests, because otherwise you won't be prepared for the exam. Multiply or divide each piece of data by a constant. The mean gets multiplied or divided by the same constant. Okay, so that's nothing new. If you multiply or divide each piece of data by a constant, the variance will be multiplied or divided by the square of that constant. All right, which is consistent with, if I just do a simple operation here, take the square root of both sides, sigma sub cx would be equal to sigma times, c times sigma x. All right, take the square root of both sides, you come up with this relationship, and that is, if you multiply or divide each piece of data by a constant, you're going to multiply the standard deviation by that. All right, that we could just test out real quick. Actually, we could test them both out. So stat edit. I got all this stuff in here. I don't want to clear it out column by column. So second plus option 4, wipe them all out. Stat edit. So let's say 1, 2, 5, 7, 8, 9. Something very simple. All right. I'll do a stat calc 1. So stat calc 1. I'm going to clear out frequency list. You could clear it out or put the number 1 in there. It does the same thing. All right, so 5 1/3 is my mean. About 3-ish is my standard deviation. All right. So now what I'm going to do, because we're multiplying here, stat edit. We're going to multiply each value in L1 by 2, for example. All right, so everything's double. I just hit second enter to bring up the last calculation, just change the L1 to an L2. All right, it was 5 1/3, now it's 10 2/3, that makes sense. It was in the neighborhood of 3, now it's in the neighborhood of 6. So, pretty consistent with what we were expecting. All right. So an exam is given, and the mean is 55, variance is 10. We double every score. All right, my new mean would be what? 110, and my standard deviation? What do we say? Oh, sorry, the variance. If it were standard deviation, it would be 20, but it's the variance. 40.
2 squared is 4 times.
Oh, it's the square.
Right, because it's asking for variance, not standard deviation. All right. Now these ones, even I sometimes have to like make up my own data set because I look at it and say, I'm pretty sure, I'm like 99% sure that this is the rule, but let me just double check. The mean is common sense, I think, but it's when you get into the variances, that's a little bit of a different story. All right, so the consequence of this rule is that sigma sub x plus y is going to be equal to the square root of sigma in x squared plus sigma in y squared. All right, so it's a Pythagorean relationship. All right, it's a little tiny connection between geometry and statistics. And you'll find, because we talked about linear regression a little bit, it's the square distances that make all the difference, because what we're looking to do is minimize the right triangle, the hypotenuse of the right triangle that would exist between, if you were to decompose the distance, or actually compose it into a right triangle, the distance between a point and a line segment. This is the same idea, it's just in one variable. All right, so something to be mindful of. Also, if you subtract two data sets, it's the same result. The plus does not become a minus. All right, so that's something very, very important. Put a star on number 8. That's going to be on pretty much every test you take in this class.